Solving a system of two equations using substitution. This video will help you review the three possible cases we encounter when we're solving a system of two equations, solve a system using substitution, and learn to recognize each of these three cases when we're solving a system. Three possible cases in a system of equations. In this video, we'll focus only on systems that have two equations. So just as a reminder here in a review, let's look at the definition of a system of equations. A system of linear equations is made up of two or more linear equations. In a system, a solution is an ordered pair that is a solution to both equations. So here I have a system of equations written down right here, a system of two equations. And we know that we need to consider both of these equations at the same time because we have this brace around there. Had I just written two equations without these braces, that means we would just simply have two different equations we were looking at. But when we put this brace around there, that indicates that we're looking at both of these equations at the same time. And so when we look at both equations at the same time, we're looking for a solution that works for both of them. And I have these equations over here on the right graphed. And if we take a look, here is this x plus 2y equals 4. There's the graph of that equation. And then here's the graph x minus y equals 2. There's the point of that graph. Now remember, when we graph an equation, what we're actually doing is graphing all of the points or solutions to that equation. So all of the points right here that occurred on this line represent a solution to that linear equation. Same thing with my other equation. This represents all the points to this linear equation. Where these two graphs intersect represents a solution or a point that will work for both of these equations. Now, we've already learned, hopefully, that we can take each of these equations and graph them, find their intersection point, and find the solution. Well, if you're taking a look here at this graph, notice this intersection point doesn't occur at a nice crosshair on the graph. So at best, I would be able to estimate that solution. Also, graphing takes a considerable amount of time to find this solution. It takes a lot of time to graph these equations and then find the intersection points. What I'll show you today is a process called substitution that allows us to find this intersection point and a solution to both of these equations algebraically. Now let's go ahead and take a look at these three cases we will encounter when we're working with a system of two equations. So the first case is that we get a one solution. Second case is that we have no solution to the system of equations. And then finally, the last case is that we get an infinite number of solutions. And if you recall, this is exactly the same type of solution situations we encountered when we were working with just one variable and one equation. Same situation here. Let's now kind of investigate how these situations come up. So the first one solution, is the most common, and that is these lines are graphed and their intersection point represents a place or a point that will work for both of these equations. And so when we have that situation, they intersect at just one point, and so we end up with this one ordered pair solution. Let's take a look at this next situation. This is a no solution case. And you can see here that I have graphed parallel lines. And remember, parallel lines will never cross. So if these lines never cross, they will never have a point in common. Since they don't have a point in common, there's never going to be a solution that will work for both of these equations simultaneously. We could find lots of solutions for this equation, lots of solutions for that equation, but none of those solutions would work for both equations simultaneously. Let's take a little bit of a closer look here so you can kind of start to recognize when you have this no solution case. I have each of these equations written in slope-intercept form, y equals mx plus b, where the number in front of x is a slope, and then the number at the end there is our y-intercept. And you'll notice when I look at these equations, they both have a slope of 1. Notice right here, it's understood there's a 1 in front of that x, so both of these equations have the same slope. Lines that have the same slope are either going to be the same line or parallel lines, and notice they have a different y-intercept. One is a positive 2, one is a negative 2. And so y-intercept, that's just simply where these cross the y-axis. So one is crossing at positive 2, one is crossing at negative 2. Anytime we have lines that have the same slope but a different y-intercept, they're going to be parallel. So if you get a set of equations and you can see that these are going to be parallel lines, you could immediately say, hey, these lines are never going to cross. There's no solution to this equation. Let's take a look at this last case. Infinite solutions. Again, this is a very rare situation, but if we took a line and graphed a line, the identical line, right on top of it, then these two lines would share all kinds of points in common. In fact, an infinite number of points in common. The only way this situation arises is if we have the same line graphed on top of itself. So here I have equations again written in slope-intercept form, and you can see that these equations are exactly the same. So anytime you have a system of equations where each equation is exactly the same, you know it's going to be one line graphed right on top of itself, and therefore we'd have infinite solutions. Now let's take a look at an example that will help you understand how to use the substitution method to solve a system of equations. And I've given us kind of some bullets here to kind of keep us on track. So I'll kind of be talking us through these bullets in this example problem. The first thing that we want to do is we want to isolate either x or y in either of these equations. So what I always do is I start and I'll take a look here at all of the different variables in my equations. I have 4 of them, 2 in each. And I'll say which one of those variables would be easiest to isolate. And the one that's the easiest to isolate is the one with the least amount of clutter around it, and that is this x value right there. So what I want to do is I want to get that x value in that first equation all by itself, and that would be step 1 here. So I'd have x plus 2y equals 5, and I want to get x all by itself. So all I'd have to do is subtract 2y from each side. So then I'd have x equals 5 minus 2y. So what I've done now is I've kind of rewritten this problem so that x is equaling this whole quantity 5 minus 2y. And the next step then you can see over here is to substitute. So what I'm going to do is I'm going to take and substitute this value or this quantity that I found x equal to back into my other equation here for x. Notice I isolated x in the first equation. Now I'm substituting into the second equation. So let me rewrite that second equation and we'll see what we have. So I'm going to have this 2, taking this equation right here, rewriting it with that substituted value in there. So I'd have 2. Now instead of x, I'm going to replace it with this whole quantity, 5 minus 2y. We already said that x was equal to that quantity, so it's okay that we're going to replace x with this quantity. So let's see, minus y equals negative 15. Notice what I have now in this equation. Now I have an equation, but I only have one variable in this equation. The only variable left is y. So I can use my normal equation solving techniques here and solve this now equation for y. So I would distribute the 2. So it'd be 10 minus 4y minus y equals negative 15. Combine like terms here, negative 4y and negative y. Okay, subtract 10 from each side. So it looks like a negative 25 there. Divide by negative 5. So it looks like we'll come over here and say that y then is going to be equal to a positive 5 when I do that division. So right now at this point I'm kind of halfway done. I've solved for one coordinate here. I've got the y value that's going to work for this system. Now what I want to do, and I just got done doing this step right here, I just solved that equation. Once I substituted, I solved that equation. But now what I want to do is I now want to solve for that second variable. And the best place to solve for this second variable is right up here where I already had isolated x. And it's always going to be that way. This setup here where we isolate the variable is always where we're going to want to substitute this back in. So if I put this 5 now back up into here to that equation for y, I'll get a value for x. So x equals, and I don't need the parentheses now when I rewrite this, 5 minus 2, and then instead of y, we're going to replace that now with the value we found, which was 5. All I have to do is do this, simplify this right side. I'm going to find my value for x. So let's see, 5 minus 10, and so then x is going to equal negative 5. So I found now both the x and y value that are going to be a solution to each of these equations. If I plugged these coordinates, and if your instructor might want you to write your coordinates this way, so make sure you ask. So the coordinates were negative 5, 5. That was kind of my final solution there. And if I plug this ordered pair, this x and y value, back up into this equation, it's going to make a true statement. And if I plug that value back up into this equation, it's going to make a true statement. So in a sense here, I found where these two lines have intersected at this point, -5, 5. Now it's time to practice using the substitution method. Go ahead and pause your video player and use these 4 steps I've outlined to find the solution that is going to work for both of these equations simultaneously. When you're done, hit play to see how you did. Okay, let's take a look. So the easiest variable to isolate is this x right out here in front. So to isolate that variable, all I'm going to do is add 4y to both sides. So I'll get this statement, x is equal to 4y. All right? So I'm going to take now, and in the other equation, notice I isolated in the second equation, so I want to take this and substitute that in for the x value in my first equation. So then it would look like this. 2, now instead of x, we're going to replace that with 4y plus 3y equals 11. Okay, now I have one variable. I can just solve this simple equation. So let's see, I'd multiply the 2 times the 4y, I'd get 8y plus 3y equals 11. So actually what I have here is 11y is equal to 11, and y is equal to 1. All right, I'm halfway done. What I want to do now is find the x value. And again, the best place to substitute back in is right over here where we isolated. I could put this y value back in either of these equations. I could have put it up here, here, but the best one is over here where we've already isolated x. So let's see. X is now going to equal 4, and we're going to replace y with 1, and so we're just going to see that x is equal to 4. And so I'll write this as an ordered pair. My solution to this system of equations is the point 4, 1. Okay, let's go ahead and practice again solving this system of equations. When you're done, hit play to see how you did. Okay, let's take a look. I'm thinking probably this x right here would be easy to isolate, or probably this x here would have been easy to isolate. Either one of those would have been fine. I'll start with this top one up here. I'll use this equation and I'll isolate for that for x. So let's see, I had -x plus 3y equals 10. So the first thing I would do is undo addition, so I would subtract 3y from each side. So I'd have this statement, -x is equal to 10 minus 3y. Now, I need to get a positive x here so I can substitute. So really it's kind of understood that there's a -1 in front of this x. So to undo that multiplication, I would use division and divide basically both of these terms by -1. All that's going to do is change the sign on each of these terms. So now when I divide by -1, my x will be positive, which is what I wanted. My 10 will be negative, and then that -3y will become positive. So here, that quantity is what x is equal to. And so since I isolated that in the first equation, I'm going to substitute that value back into the second equation. So let's see, I have 2 times now -10 plus 3y plus 8y equals -6. Okay, distribute the 2. Okay, looks like we can combine some like terms here. The 6y and the 8y would give us 14y. So I'd have -20 plus 14y equals -6. Okay, add 20. Okay, 20 plus a -6. That's going to give me 14. So divide both sides by 14. And we'll see that y is equal to 1. All right, we're going to substitute the y value now back up into this equation. So I'll have x equals -10 plus 3 times 1. All right. Let's see, x is going to equal basically -10 plus 3. So -10 plus 3 is going to give me a -7. Okay, so our solution to that one then is going to be -7, 1. Now let's take a look at solving a system of equations again using substitution. But let's start to identify now these 3 cases that we're going to come up with. You know, It's easy to see these three cases when I graph a picture to see if the lines are going to cross at one point, if they're parallel, or if it's the same line. But it's harder when we're solving an equation or solving a system of equations. So we're going to want to look for some kind of clues and cues here that will tell us which of these types of situations we have. So go ahead and solve this system. We're probably going to get some fractions because look here where these points cross. They don't cross at a nice whole number intersection. So it looks like we're going to get some fractions here. Solve this one. When you get done, hit play to see how you did. Okay, probably easiest to isolate this x right there. So all I'm going to do is add y to both sides. So I'd have x equals 2 plus y. Now this quantity, we're going to substitute that back up into the other equation for x. So that's coming right up in here for x. Let's come over here and see what that looks like. So that I'd have 2 plus y in place of x plus 2y equals 4. All right, I don't have anything to distribute or multiply there, so really I just have this, 2 plus y plus 2y equals 4. Combine my like terms, y plus 2y would be 3y. Okay, subtract 2. So I get 3y equals 2, and now here we're going to get our fraction. Divide by 3, divide by 3, and you see that y is equal to 2/3. Okay, I'm halfway done, and again, we're going to want to substitute that right up here where we already isolated y. So our x value then is going to be this, x equals 2 plus my y value, which was 2/3. Well, I don't think there's any real reason to write 2 as a fraction and try to make this one whole fraction, because really just 2 and 2/3 is a pretty nice value that would allow us to graph this point if we wanted to graph it. So I think we'll look at it just like that and stop right there. So we get this ordered pair 2/3 and 2 and 2/3. And you can see why this value would have been difficult to get from the graph up here. You know, 2/3 and 2 and 2/3, it kind of looks like that, but again, with the graph we would have to estimate. Here, solving with substitution, we get an exact value. Now let's take a look at a second case scenario. This is a case where the lines are parallel. So here we're going to have a no solution. But let's go ahead and solve this using substitution and see what happens, so that later on when we're solving one using substitution, we can recognize this event is happening, and so we can say then that the system of equations has no solution. So go ahead and pause your video player and start to solve this system of equations and kind of see some funny stuff's going to happen. Go ahead and take a look and see what's going to happen here. Okay, well, it's easy to isolate one of our variables. Y is already isolated. So all I really have to do now is take this quantity x plus 2 and substitute it down in the other equation for y. So here's what I would get. I would have this statement then, x plus 2 equals x minus 2. I have just one variable in the equation, so I would go ahead and solve this the way I normally would. And so notice I have variables on both sides, so I try to get rid of the smaller variable term. Well, they're both the same. So I would subtract x. The variables are going to drop out now on both sides. You know, x minus x is 0 and x minus x is 0. So the variables have dropped out, and I'm left with an untrue statement, right? When this happens, when we're solving using substitution, variables go away, we're left with an untrue statement. We're going to get no solution to our system. The convenient thing about this is that this is exactly the same thing that happened when we had just one equation and there was no solution to a one equation situation. The variables dropped out and we were left with an untrue statement. So that situation comes up both times, whether we're solving a system of equations or just one single equation with one variable. The time that we get no solution is when the variables drop out and we're left with an untrue statement. It's not enough to stop here. We want to make sure that we identify this system of equations has no solution. Now let's take a look at this third and final case. This system of equations has infinite solutions. Notice this is going to be one line graphed right on top of the other. They're going to share all kinds of points. So we are going to get infinite solutions to this equation, this system of equations. Go ahead now and solve this system of equations and see what kind of funny stuff happens here, so that later on when you're solving a system you'll be able to recognize it and be able to identify it as an infinite solutions situation. Okay, y is obviously easy to isolate. It's already isolated. Y is equal to x plus 1. So we're going to plug that right up into this equation there. So it'll be 2 times x plus 1 is equal to 2x plus 2. Let's see, I distribute the 2. 2x plus 2 equals 2x plus 2. You can see already that we're getting an identity here. The left and right side are exactly the same. But let's say we didn't recognize that at this point. We'd say, all right, get the variable terms to one side, get rid of the smaller one. Well, they're the same. So when we subtract them, they're going to drop out. Notice our variable terms have dropped out entirely. But notice this time, we're left with a true statement. 2 is equal to 2. So when we come up to this situation, variable terms drop out and we're left with a true statement, then we know that we have infinite solutions. Again, this is very convenient. This is exactly the same scenario that happened when we had one variable and one equation. If the variables dropped out there and we were left with a true statement, we had infinite solutions there as well.